Buenos días, voy a hablar en español en introducción. Agradezco mucho la invitación a Carmen y a Carlos a este evento. Muy fructífera reunión y me da mucha alegría que sea en vivo, la primera práctica en vivo que hago desde 2019 y esperemos que así siga, ¿no? Que lo virtual sea no por obligación. So, this is part of our research project that Lourdes and I have since 2020 about the deductive aspects of logic from computer science to philosophy. And here, the modal aspects at the end, it goes as cues. I'm going to talk maybe about formal proofs in natural deduction, because this is a history event, and then I decided to stay the first part in some very interesting historical facts. So, yeah. Jaśkowski is a Polish mathematician that now we say that invented natural deduction together with Einstein. The style of formal proof of Jaśkowski, which is the one I'm going to talk about here, at the end, today is not important for researching proof theory, but it's the mainstream for teaching. Einstein is the one that is, we still do research in this style. Yeah. So this is the first paragraph of Jaśkowski's article, 1954, which is called The Rules of Suppositions in Formal Law. I'm going to read it. In 1926, Professor Łukasz called attention to the fact that mathematicians in their proofs do not appeal to the thesis of the theory of deduction. The theory of deduction is Hilbert's mathematical system. While make use of other methods of reasoning, the chief means employing the method is that of an arbitrary supposition. The problem raised by Mr. Łukasz was to put these methods under the form of structural rules and to analyze the relation to the theory of deduction. The present paper contains the solution to that problem. Only because I cannot avoid it, at the same time, Gensen present these two articles, or an article in two parts, and he introduces natural deduction as a system intended to capture natural mathematical reason. There is no relation between Gensen and Jaśkowski, no mention. So, I'm going to talk here about the diagrammatical system, because this is the mystery. The diagrammatical system of Jaśkowski, of course, is false indentation. So C is identification, N is negation. Is only in a footnote of the article. He says that he developed the results about the Łukasz question in 1926. He presented them in a congress, the first congress of Polish Mathematical Society in 1927. And he said that the results are mentioned in the proceedings, which were published in 1950. At the end, the proceedings only have the title of Jaśkowski's book, not an article. If you know, if you're familiar with natural deduction, but this is at the end Fitch-style. Yeah? So a box here, a rectangle, it's opened with an assumption. In this case, this is the proof of the contrapositive, of one of the contrapositives. In this case, not P implies not Q. Then another proof assuming Q. and so on. At the end, the fact that not P implies not Q implies P equals Q is this is something, but this is theory. It's proof. Yeah? That was 1934. And the seminal work of Fitch is 1952, the work on symbolic logic, where he introduces a diagrammatic system. And one thing, there is no explanation about how to read these diagrams, Jaśkowski. He only says, I use this format in 1926, but in the article he uses a non-diagrammatical system. So, Fitch introduces the system with boxes or lines or indentation in 1952. He barely mentioned that the system is based in Jaśkowski's and Metzgen's work, only in the introduction in a footnote. And here the central notion is that of subordinate proof, which is a subordinate proof is triggered by making a temporal switch. And to keep track of these subordinate proofs, he uses lines, and we now use boxes or indentations. We open a box with a temporal assumption and close it by discharging. Important here is we close this assumption. We discharge the assumption. Yeah. And then he also treats modal logic and introduces a second notion of subordinate proofs to handle the box modal, which are called a strict subordinate proof. Perhaps because he mainly speaks of the strict implication.
Fitch is the first one with this assumption within classical deduction of the one.
Fitch, you said
the first one.
Yeah, the Fitch that systematically introduces and explains the system. Yeah. So now our aim is to mechanize this kind of diagrammatic algorithms. Yeah. What is mechanized? Well, in our sense, is to write the mathematical results in a proof system, in our case, the top proof system, and to develop the proofs. Yeah. So this is part of the code. Here we have a definition of the inference rules. This is exactly this rule here, which is implication introduction. And here we are using sequence type. Because sequence type is very easy to mechanize in this. Yeah? So the judgment here, yeah, the proof is exactly this. Here we have to count, but that's not important for this. And then we have this theorem, which is the fact that this rule here, which is the composition or substitution rule, also called the good rule in sequence calculus, is admissible. And here is the proof. So this is a computer-assisted proof in the modern sense. It is not one proof that I write information, then I press enter, then I go to take holiday, 1 week, 2 weeks, 1 month, or maybe only 3 hours, and then I come back and the computer says, yeah, it's true. Yeah, it's true. No, this is completely interactive. I say, prove this, the computer says, yeah, okay, you need to give me a proof of this and this, and I say, okay, the proof of this is that, and so on. This is completely interactive. This is our purpose, but we are not going to talk about this. So, this is an original diagram in Fitch book, a proof with lines. So this is an assumption. You open another subordinate proof assuming Q, a third one assuming P, and the important thing here is something that it's weird for the white or black hole practice, which are these steps 4 or 5. It's repeating the information. Yeah, this is called the reiteration. And the question is why is repeating information? Yeah. This is a proof in a more modern style, including already the other connectives. Here is classical logic. For example, we have here that we assume not R, and here again we are repeating information. And then we derive not Q and Q. Then this is a contradiction, and then we can conclude R. And the important thing here is that we close the information. So outside of this box, we cannot use any of this information to make more conclusions. Yeah. Well, these are the original diagrams presenting the inference rules of Fitch. So the implication says assume P, do something, which is the analysis here, and obtain Q, arrive to Q. And these are similar ones of quantification equivalent. Assume P, arrive to Q, then assume Q, arrive to P, then they are equivalent. And one important thing that I'm going to say quickly is that here, for example, there is no ellipsis, which is wrong. Because which is wrong. No, the ellipsis. Yeah. Because, for example, here, which is that simplification, here is a conjunction, and then after some other steps, it's this paragraph. And the same with modus ponens. Let me see. Yeah, 2 and 4. Most ponens of this and this. And this, the premises modus ponens are not together. But this is not given by the diagram. Yeah. So one can think that these need to be together in order to obtain the conclusion. But it's not given by the diagram. In a modern version, the implication introduction rule is not like this. Yeah? It's exactly, it's more or less the same. But the important thing that, and this is a quote of this book, is to conclude A implies B, it is sufficient to make the temporal assumption A and to arrive to B. And the diagram also gives a sense that first I need to have A and then do something and finish with it. Yeah. So it seems that the diagram takes deduction and proving procedure. Yeah. So about this repetition of formulas, which for me are quite strange, but they are quite useful and usually natural reduction is studied in this way. So I can say maybe it's a controversial claim that the reiteration rule, but in the practice we just put an assumption and we use it repeated times. We are not saying again, we prove the assumption again, we prove the assumption again. Yeah. So, and the reiteration rule is in some sense saying, well, I am repeating already known information, but I am stating it in the format. Why? So I can say, we can say that this rule derives from the proofs of it. Because I only put the assumptions at the beginning of the proof, and then I can use it several times. It turns out that the rule is not needed, but it's an aid, a visual aid to match the diagrammatic representation. And well, the example why should I break it or not is the proof of the positive paradox. Yeah. So A implies that B implies A. So here is a proof in Fitch books. So I assume P, then I assume Q, then I repeat P, and since I start arguing in Q and arrive at P, then I conclude Q implies P. But this is only because of the reiteration. Yeah. This is the profile of Jaśkowski's diagram, and it's exactly the same with Fitch. Yeah, this is another problem, but this is the central issue. Yeah, the question and the mystery here is that Jaśkowski only says, I use these diagrams, but now I'm not going to use them. I use these diagrams and I talk about them in the comments in 1927, and they are mentioned in the proceedings in 1929. No, that proceedings, it's only the title. This is a proof of the positive paradox, which is mysterious for the visual point of view. It says, okay, assume A, immediately discharge B, but B was never assumed. Yeah? It's a rabbit out of the hat. And it says, okay, this is by implication introduction of step 1. Plato says, but there is no elaboration on that. Yeah, it looks weird, but it's not that weird if you say that you use B 0 times. You discharge B 0 times. Because there are other examples where you use the assumption 2 times, for example, to prove the contraction. Yeah? It's not that weird. Of course, if we are teaching, which is very important to do this is really weird. This is difficult to get. And this is not for Plato, this is not in Fitch. Yeah? Fitch uses reiteration. He says that, Plato says that, well, my presentation comes from Proud's 1955, a book on symbolic law in Swedish. And, but for me, and to teach is really difficult. Here, of course, is the,
yes, from 1 to 2, how are you allowed to pass with implication in production?
Yeah, that's exactly the point. Because you assume B 0 times. You assume B 0 times. There is no assumption of B. But you can discharge it.
You introduce B without where is it?
Yeah, maybe I think I can delete this, yeah. It was the change for today. Maybe in modern notation, it's the rule something like this. Yeah. So here you say, of course, the brackets are going to discharge here. Okay. And then the label here, it's fake. Yeah. I discharge the hypothesis label 1.
You discharge A. Okay.
Yeah. But there are n occurrences of A, the multiplicity of n. Then when n is 0, is this case.
What you write from A, you have a derivation of B, and then you can implication introduction B and from B. But here you don't have a derivation from hypothesis A to B.
This is the A instance here. Here there is no discharge, there is no label. Yeah, it's. I am quite happy that it confuses you because it's really hard, even for me. Maybe I can continue and we can talk later. And this is not from Rabbits. This was known to Gensen in 1935. This is the proof of positive paradox in Gensen's 1935 article. And it's the same, only this is Fitch-style, of course. I assume A, I discharge B, which I did not assume. This is Paul and theorem in education introduction. No label, no discharge. One discharge, we call it. And then I discharge A. Yeah? By the way, there is no explanation against because he only puts this derivation. Yeah? Okay. This is except this part. This is part of the footnote of Jaśkowski. Here is the proof of the contrapositive, and he said certain expressions. Here is the Q, then not being implies not Q, repeated here, which have been written outside of some rectangles, have been repeated inside of them. We obey a particular rule, which now, through the modification of others, has become superfluous. So he says, I have to go quickly. He says, it's not me. But in the paper, he speaks about this kind of things. And here we can say the truth is because it's the second assumption of another proof, which is part of. And here I can read the S is for supposition. Here it says not being implied on Q is the second supposition of the proof. And then Q is the first supposition that depends on the second supposition. And then not P is the first supposition that depends on the first supposition and the second supposition, and so on. Yeah? But the point here is that the rules that he speaks about, these are the rules of the article, and these are two of the rules. So this is the implication, introduction, and contradiction, reductive. Observe something. Here, value means already derived. Yeah? He says, if in the domain D of a supposition alpha, a proposition is a type, beta is valid, I mean it's previously derived, it is allowed to subjoin a proposition of the form A implies B to the domain where B is an immediate subdomain. But he never says we discharge alpha. He never says we cannot use alpha. The same happens in this part. So this is a proof of the paper. And observe some things. Here guessing is P, which is step 1. And for example, here, rule 2 is implication inclusion, rule 1 is assumption, rule 3 is multiple, rule 4 is contradiction. Here, he says, I assume Q, and then immediately he says, okay, then Q implies P because of the step 1. But it's not the diagrammatical issue of I started at Q and I write at P because P was here. The same happens with this contradiction. It says 8. I assume not P, then I have Q and not Q, but Q is before the assumption of not P. Yeah? This doesn't correspond to the type. So now for the modal part, and for our in A, which is has not changed. This is a proof of string implication property, but Fitch uses now two kinds of subordinate rules. Yeah, the ordinary one and the one that is called string. Yeah. So, for example, here is an assumption. So this is a subordinate rule. It is a box indicating that it's also a string for a string. So I have to work with it. This is the model version that we are considering. Of course, we have here diagrams, and this, for example, is a reiteration rule. We have previously box A, and then we open a box indicated by this lock, and then we repeat this formula. Yeah, these are computational interpretations, and but the point that this is clearly a reiteration rule. This sort of, because it's not this is not repeated, but it's A, the one that is repeated. Well, we can give intuition using more critical words. To open a box is to say I'm going to an arbitrary word, and to close the box and say, okay, I return to the current word. This is a proof. This is the kind of Fitch-style proof that we want to make. Here we have a rectangle, which is ordinary subordinate proof. Here we have a log. This is a strict subordinate proof. Observe that the first step in this strict subordinate proof is not an assumption. So this is something important for mechanization. At the end, if we only have subordinate proofs, ordinary, we don't need the diagram. Because we know that if we introduce a new assumption there, then a box starts. But with this now. And if we want to mechanize in the sense that I already mentioned, this is a version with sequence, which is, I think it's quite straightforward to see that this corresponds to this. You say, okay, these are the assumptions, then I open a box, a model box, then I arrive to A here. Then I can close the box and compute box A. And the box of the diagram and keep the box of light. But we don't want to mechanize this. We want to mechanize this. Yeah? And we can say, okay, there are equivalents. Yeah, but if we want to mechanize equivalence, then anyway we need to mechanize. Yeah. So, what is the derivative for this project? To keep the intuition of the reason, and to develop a proof that we call transition in a work with quite final course this year, which is a proof that conjugates two social rules. A proof that is understood by the experts in the theory, but also by the experts in the proof system, in the computers, in the program. Yeah? So, it's not a proof that gives guarantee, but gives also, then also to give explanation. Yeah? This is the name of a Robson article. It says proof equals guarantee plus explanation. Yeah? And we need to model unfinished proofs, which was not in the previous work we have faced. So to do this, we have, of course, faced in previous work with this definition of proof, which I'm not going to read on this scale. The important here thing is that the proof now is a mathematical structure. Yeah? So a proof figure is a mathematical structure, which T is the number of steps in the proof. This function f, it says which formula is at each step. And these intervals are modeling the boxes, the diagram. Yeah? And there are two kinds of intervals. If it at infinite, this is merely a notation to say that the box has not been closed. Yeah. This is a proof figure. Of course, not any proof figure is a legal proof. Some proof figures are, we call them pseudo proofs, that say that the steps, the formulas, are according to the infinite rules. Yeah. And well, we say that if we compute C, then we have a set of proofs depending on gamma, we write this. Of course, the final formula is the one we want to prove. And this is the last slide. At the end, we define proof as a special pseudo proof, which at the end says all boxes are. Yeah. But the important thing here that I am not, we are beginning to discuss many rules and lines. This is a mathematical question. Why? And these are my computers say, okay, this is a mathematical structure, and then can be mechanized in multiple using a structure in the programming language, a class or a record, and so on. And this way, is very the arguments in the paper are translated to the language of the proof system, and we can generate this kind of proof transition. And then this is my last bullet. I ask myself if this notion of proof will be relevant for in the philosophy of science, of course in the structural. This is here now on the question. Muchas gracias.